Good morning in advanced chemistry. Today we're just going to start touching on learning target 3.4, which says we're going to describe equilibrium in a reversible chemical reaction. That's what we're going to do today. Later on we're going to do the second part of that statement, which is to understand what's called the equilibrium constant and its relationship to the direction a reaction is favored. So we're going to wait on that, but today we're just going to talk about what is chemical equilibrium, what does it mean, and we're going to start by talking about reversible reactions. So a reversible reaction is a type of reaction that can actually take place or takes place. Reversible reaction is one that takes place in both the forward and the reverse reaction simultaneously. So at the same time, the reaction is going both forward and backwards. Now, we have talked up to this point as a chemical reaction, you mix some reactants together, you let it happen, and you make a product, and then you're done. Well, unfortunately, that is not exactly the entire story. So I have been sort of misleading you up to this point in your chemistry career by telling you got reactants, they make products, booyah, you're done, yay. That's not really what happens. Equilibrium means balance. So balance is everywhere around us. For example, if you were ever scared by Mr. Rissy when you talked about ecosystems, where maybe you have a population of, well, we're in Michigan, so let's say deer. Here's my deer. It's a buck. And he lives in the woods. Well, you're going to get to a point where if you start to have more and more deer, these deer are going to compete for food, water, shelter, resources, etc. The more deer you have, the fiercer that competition is going to be. And so to restore equilibrium in an ecosystem, what happens is maybe some of those deer die off by disease or predator, and it keeps that balance in check. It reaches what's known as a carrying capacity. So that's an equilibrium. The deer population goes down, it might go down a little bit too far, and then it gets restored, and you have a few more deer, but it kind of stays at that same level. That's balance, that's equilibrium. In a chemical reaction, you also have balance, you also have equilibrium. I'm going to show you I have SO2 reacting with oxygen gas to produce SO3. And so what you guys have thought of so far in a chemical reaction, you should pause for a second probably to write this reaction down. What you've thought of so far in a chemical reaction is that you just kind of mix these two things together and presto changeo, they make SO3. And then you're done. And that's not really true. So what happens is that, yes, some SO2 and O2 mix together, and this is not balanced, it's going to drive me nuts, 2 and 2. 2 molecules of O2 and O2 mix together, and will make SO3. But as soon as SO3 is present, as soon as it's there, because you're going to start that reaction with no SO3, you're going to start it with just those two things. But as soon as some SO3 is made, it is going to start decomposing back into SO2 and O2. And so what you have is a reversible reaction, one that is occurring both forward and backward at the same time. Now they don't have to occur at the same rate. So for example, once you start this reaction, the forward reaction might be going really, really fast. You might have a rate of 1.0 times 10 to the negative 1 moles per liter second. And the rate of the backwards reaction might be really slow. It might be 1.0 times 10 to the negative 6 moles per liter second. So you are making much more SO3 than you are using up to go backwards. So if you were to show this maybe by drawing arrows to represent magnitude, for every time that you go and make SO3, you are only making a teeny tiny bit of the reverse reaction. So those rates are not necessarily always the same, but at equilibrium, they will be. So what's going to happen eventually, remember that the initial rate is going to slow down with time. So this arrow is going to shrink over time. As that big arrow shrinks, as it slows down, as SO2 and O2 are used up, the rate of SO3 might speed up to a point where eventually the forward and backwards reactions are going to take place at the same rate. So for every one time that you have SO2 and O2 combining to make SO3, you're going to have SO3 going backwards to make reactions. So what that's going to look like is that no change is taking place. So it will seem like the reaction is ending, but it's not. It's not truly ending. All that's happening is that the forward and backward reactions are happening at the same time. So a reaction that happens both in the forward and the reverse direction simultaneously is known as a reversible reaction. Let's talk about what equilibrium looks like. Equilibrium, by definition, is when the rates of the forward and backward reactions are equal. So what this means is that the concentrations of all your species will not change. Okay, so once you reach equilibrium, whatever the concentration of your species are at that point, that's where they will remain as long as equilibrium has been established. So let's take a look at what this looks like with our example. So we had 2 SO2 combining with O2, making 2 SO3. And remember, this is reversible. So let's think about what happens in this reaction. I'm going to have a graph here. And on the x-axis is going to be time, so as time passes. And on the y-axis is going to be concentration. And that's going to be in moles per liter. So let's talk about what happens to the concentration of SO2 during our reaction. I'm going to use orange for SO2. So let's pretend that we start off with 1 mole per liter of SO2. The amount of that SO2 as the reaction starts, it's going to immediately start to combine to make SO3 with O2. So its amount is going to drop off and the rate at which that reaction goes is going to kind of slow down. Remember, it's getting used up, so it's not going to be as much around to collide with oxygen correctly. Now, oxygen is going to do the same thing. I'm going to use yellow for oxygen, and I'm going to say that we use a little bit more, so 1.1. And oxygen is also going to get used up, and as it gets used up, the rate at which it's getting used up and going in the forward direction is going to slow down because there's less of it to collide with SO2. Now let's compare that to our SO3. So I'm going to call this. SO3 is going to start off with nothing, because all you're going to have to start is SO2 and O2. But as the reaction progresses, you're going to start to make SO3, make it. Now you're going to get to a point where it appears as though no more SO3 is made, and it's just going to level off. And you're also going to get to a point where it appears as though no more SO2 is used up and it levels off. Likewise, you're going to get to a place where you have no more changing concentration of your, I forget what I said, the other reactant. When all of those species are no longer changing, that is what is known as equilibrium. So equilibrium is established right at this location right here. At this moment in time, where the concentrations are no longer changing of those species, it is at equilibrium. So we could even make a guess as to what those concentrations are. So for example, it looks like this, whatever orange is, let's say that orange is, I can't remember what I said initially and I apologize. Let's say orange is your SO2. And let's say the concentration of SO2 right here, it looks like it's right around 0.5. And your O2 is maybe 0.7. And your SO3 is 0.6. Just rough estimates there. So at equilibrium, those concentrations no longer change. So even though that O2 is 1.1 to start, once it gets down to 0.7, it's going to appear that the reaction is, quote, over. But it's not over. What's really happening is that it's just for every time that the products are made, the products are being used to create the reactants again on a one-for-one basis, so that nothing changes anymore. You don't get any additional product because it's immediately used up to make reactant. So that right there is your equilibrium. Now I want you to notice a couple things. Number one, the species concentrations are not changing. Number two, the concentration of the species are not necessarily equal. So that's an important one. Just because they're at equilibrium, which kind of sounds like equal, it's equal rates, not equal concentrations. So I'm going to just say concentrations do not have to be equal. Okay? That is not a requirement for equilibrium. All that is a requirement for equilibrium is that the rate of the forward and backward reaction is equal, which means your concentrations do not change. Those are your requirements. So that's why we've been talking about rate. Okay, let's add in one more thing here. What equilibrium really means. Number one, it's dynamic. The reactions continue to occur in both directions after it has been established. So it is occurring in both the forward and the reverse reaction at the same rate. So the products of the concentrations of the products and reactants do not change over time. And I'm going to add up here at the same rate. Now, this is kind of out there, and I'm hoping that when we see each other next in class, we'll be able to kind of do a visual demonstration of this, so in addition to what we have. What I would like for you to do right now is take a look over your notes and write down one specific question that you have regarding equilibrium or something that you've seen on these notes. And I want you to write it down, and then on Monday, I'm going to collect those and we'll talk about them. So write down one question for me, and we'll talk about them next time we see each other. Thanks a lot. Have an awesome day, and I'll see you soon. Bye.